All right, I'm Thomas Morel of the Communication System Project, and this is a demonstration of how the system works. This is the transmitter end model with the Pluto transmitter. We'll be taking an image from a file. We are just going to take one of the colors. It's a black and white photo, so all the colors are the same values. Do the data processing, send that to the frame builder. In the frame builder, if I can zoom out and zoom in, there we go. Builds the frame. So the frame model is, let's see, 26, well, it's 13 bits on the frame. It's really 26 because it's a 2-bit modulation scheme. It's QPSK. Then we have 16 frame number bits, which tell you which frame out of the total frames this one you're receiving is. Then we have the value of the total number of frames and the total data transfer for 16 bits. 4 bits is the encryption key number from the array of encryption keys that we have. Next is the amount of data bits that will be used out of the entire data bit part of the frame. That will be 11 bits long. Then we have the actual data, which has, not 1529, it has, I think, 1541, yeah, it's 1541 bits, not 1529. After that, we have the checksum, which is now 12 bits. So over here, we build that. First, we take the frame number that we have, then we have the total frames, then we add the key number, then the length of bits that we're using through the data portion of the frame, then the actual data itself padded with zeros to fill out that frame. That's all added to one long message. Then over here, we sum up all the bits in that message for the checksum, and then we add that to the final part of the packet. Then here we add the Barker code, modulated through QPSK, put through a raised cosine filter, and then that gets sent to the Pluto. We're using the 2.4 megahertz band for ISM with a gain of 0, so we're just getting directly out from the Pluto itself. With a sample rate, baseband sample rate of 180 kilohertz. Yeah. So, for now, I'll just run the transmitter while I go to the receiver, make sure that compiles. So the receiver will be on the other side of the dorm at a somewhat realistic distance. I'd say it's about 20 to 30 feet. Here we have the receiving SDR at the other end. For demonstration purposes, I'll start off with running it to see that we get the picture on the other side. So here is our constellation, and boom, we got the picture. And then, so once we get the picture, the program stops. But if we just clear everything, run it again, we should get it again. The transmitting, there we go, beautiful, just for to show that it's repeatable. So here we have the receiving end, same thing, except now we have the frames that spits out the frames. Sorry, the frames are 1800 bits each. And it goes through all of the processing, square root filter, into the frequency compensator, into the simple synchronizer, into the carrier synchronizer. Then we have automated gain control that just sets the gain to 1. So we match up with the constellation very well. That goes into the frame synchronizer, which finds the Barker code and gets the rest of the frame from that. Then we go to data decoding. In data decoding, it first matches it against the Barker code to do a final phase correction. And then over here, we get the complex phase shift from that and the QPSK demodulation, then it descrambles. And after the descrambler, we go to breaking down the frame. here, let's start at the bottom. This just selects the decryption key number from the frame, and as you can see, it's correct. It's 11. Right now, we don't have the decryption working in the current frame setup just because don't have time. Hopefully by class tomorrow, I'll be able to hand that in. Here we have the checksum. So all this does is sum up all the bits and then compares it to the checksum that we received. If they're equal, it sends out a Boolean true, which enables this frame check subsystem. All the frame check subsystem does is allow for the data frames to add up in order. So let's say you get the first 3 frames come perfectly, then you miss the 4th frame, you get the 5th frame. The program will wait until the next transmission, until you get the 4th frame, and then it'll keep going. This is to make sure that the image is synchronized. After that, once that works out, this is a Boolean, which enables the frame decoding subsystem, and this selects the data bits from the entire data bit portion of the frame. Then it goes into the video decoder, which just reconstructs the image frame from the stream of bits and sends that out to this output, which then goes out here into the RGB. Then the RGB is directly connected to the video viewer, which we just saw. Here is the stop function that stops the simulation once we receive our image. And here is our frame rate. Right now I have it at 1 frame per second, but since there are a few missed data frames in the reception, it's a little less than that because of the error. But yeah, that is a demonstration of our total communication system.